Our next theorem simply states that if S is a non-empty subset of the real numbers and it's bounded below, then it has a greatest lower bound, or an infimum. The proof uses axiom 12 and theorem 0.19. And it's worth noting, or at least worth thinking about. Let's say you have a set S, and let's say that it is bounded below if it's bounded below, then consider a new set S prime where you take all of the elements of S and you negate them. That set is going to have an upper bound and a supremum. And that's part of how the proof works out in theorem using theorem 0.19. Theorem 0.21 is it looks very simple, but you can see the proof in the text. It goes using those steps, those axioms to prove it. If x is a real number, then there's an integer in such that you've trapped x in between two integers, in between, so to speak. X, it can be greater than or equal to this one and less, strictly less than that one. So just simple examples. If x is 5.5, 5.5 is caught between the integer 5 and 6. It's less than 6, strictly, greater than or equal to 5. X is negative 2.1. We've got it trapped between the two consecutive integers, negative 3 and negative 2. Strictly less than negative 2, greater than or equal to negative 3. And the last one was a border case. It's an integer. X is negative 10. It's caught between negative 10 and negative 9, where it's strictly less than negative 9, but it's greater than or equal to negative 10.